All right, guys, it's time to move on. We are now moving on to chapter 4, which discusses my favorite topic in math ever, differential equations. This is an entire field of math. So if you like all of this stuff, you can actually do this for like your job. You know what I mean? It's really cool. So let's define what they are and see what I can do with them. So starting, of course, with section 4.1, the basics of these things. First things first, let's define what it is. It is an equation involving an unknown function y and one or more of its derivatives. A solution to a differential equation is a function y that satisfies the differential equation when f is substituted into the equation. So equations we have seen before have all been us trying to solve things for like an x, right? So like equations we have done is like x squared plus 12x plus 35 is equal to 0, right? These are the equations we normally do in which I'm solving for x and I get like a number for x, right? That's what I have done up until now. With these types of equations, though, I'm not solving for a number, I'm solving for a function. Okay? So, once again, the whole point is I'm solving for a function. That's what I want. So, looking at some examples, like this first one right here, an example of one would be y prime is equal to 2x. So what this means is I want to solve for something y. I want to know what function y is such that y prime is equal to 2x. The solution is going to be the function y equals x squared. Because if I plug this y into here, it'll be right? Because if y is equal to x squared, y prime would be 2x, which is what it was, right? Now, this one isn't very hard. We are going to see some that are way harder, but that's just to show you what I mean. Another example would be like this one right here. Y prime plus 3y is equal to 6x plus 11. Again, I want to solve it for y. What y would make that true, right? And if I were to plug in the function y equals e to the negative 3x plus 2x plus 3, I would see that's right. This is what I would plug in here for y and make that true. Same thing over here, y2 prime minus 3y prime plus 2y equals to 24e to the negative 2x. The y that would work in there is this y over there. So what I want to focus on in chapter 4 is figuring out how to solve these things, right? How do I get that? How do I get from this equation over here, solve it for the y, and I get this? That's what I want to know, okay? So first things first, example number 1, verify that the function y equals e to the negative 3x plus 2x plus 3 is a solution to the differential equation y prime plus 3y equals 6x plus 11. So the second one, right? Show me that that's true, okay? For example number 1, there we go. The differential equation I'm working with is y, this is example 1, y prime plus 3y equals 6x plus 11, and it wants us to verify that that must mean y is equal to e to the negative 3x plus 2x plus 3. So the idea is I want to plug this in for the y over here and show that I get this, okay? So first things first, I need to know what y prime is, okay? Because there's a y prime, so I need to plug in the y prime, so I need to use y to get y prime. So the derivative is what I want. So the derivative of e, remember we said e just stays e, right? So this is just going to be e to the negative 3x. But by the chain rule, I need to multiply that by the derivative of negative 3x. Well, the derivative of negative 3x is negative 3. So chuck that in there. The derivative of 2x is just 2. So plus 2. And the derivative of 3 is 0. So I am good there. So now I have y prime and I have y, so let's plug it in. Y prime was negative 3 e to the negative 3x plus 2 plus 3y. Y we said was e to the negative 3x plus 2x plus 3. So let's simplify this. Distribute my 3 over here, whereas with this one, nothing really happens, right? So this is going to just say negative 3 e to the negative 3x plus 2 plus 3 e to the negative 3x plus 6x plus 9. Combine like terms, negative 3 to the e, try that again, negative 3e to the negative 3x plus 3e to the negative 3x cancels out. So I just have 6x and then 2 plus 9, 11. Which, look at that, is what I said it should have been. So this is what I mean by y being a solution. It's that if I plug it in, I work out. So example number 2, I can do the same thing. For example number 2, it wants us to verify that the function y equals 2e to the 3x minus 2x minus 2 is a solution to the equation y prime minus 3y equals 6x plus 4. So this time I'm verifying the solution to y prime minus 3y equals 6x plus 4. Verify that the solution is y equals 2e to the 3x minus 2x minus 2. Okay, so again, the idea is I want to plug this y into here, which means I need y prime here. The derivative of 2e to the negative 3, 2e to the 3x. Remember we said e just stays e, but then by the chain rule, I need to times that by the derivative of 3x. So then looking at just the e part, it would be 3e to the 3x, but I'm saying that times 2, which would make it 6. So 6e to the 3x. The derivative of negative 2x is negative 2. The derivative of negative 2 is 0. So I'm good there. So now plug everything in. Y prime we said was 6e to the 3x minus 2 minus 3 times y, which was 2e to the 3x minus 2x minus 2. Distribute my negative 3, 6e to the 3x minus 2 minus 6 e to the 3x plus 6x plus 6. Combine like terms, 6e to the 3x minus 6e to the 3x cancels out. I'm left with 6x. Negative 2 plus 6 is positive 4. So that works out. So again, this was just to show you what I mean by wanting to solve it for the y. I want to know what the function would be that I can plug in here to make it true. That's what I want. There's another term we need to know. The order of a differential equation is the highest order of any derivative of the unknown function that appears in the equation. So what I mean by that is look at how many derivatives I'm going to have to take, okay? So looking up here at the first one, y prime. That means I'm going to take the derivative one time. So the order is 1. This one goes y prime plus 3y. The highest derivative there is y prime, so it's 1. This next one over here, y2 prime minus 3y prime plus 2y. The highest derivative there is y2 prime, so it's 2. So looking at example number 3, 3a is 4y minus 4y equals x squared minus 3x plus 4. The highest derivative there is y prime, right? That's the highest one. So the order here would be 1 because it's just y 1 prime. For part B, I have x squared y3 prime minus 3x y2 prime plus xy prime minus 3y is equal to sine. The highest order of prime I have there is y3 prime, so the order is 3. Easy enough. For part C, I have 4 over x y4 prime minus 6 over x squared y2 prime plus 12 over x to the fourth y equals x cubed minus 3x squared plus 4x minus 12. The highest one there is y4 prime, so the order is 4. The order is going to kind of determine how I solve them, and so it is a big deal to know how to find it. Okay. In this class, I don't think we go beyond y prime as far as solving for the y, so it's not really something you have to worry too much about. But as you go on and take more math classes and that kind of thing, you are going to need to know how to solve things with 2 prime and 3 prime and 4 prime and all of that. So knowing it is very, very helpful. All right, there are two kinds of solutions we are going to solve for. The first one is the general one. What this means is that it gives us a basic format for every solution y could possibly be. Now, you may be thinking, wait a minute. On the examples we saw before, there was only one y. So what do I mean by any possible y, right? Well, think about this one up here. If y prime was equal to 2x, we know that then y must be x squared because this y prime would be 2x, right? But think about this too. What if this was y was equal to x squared plus 2? Y prime would still be 2x, so that one still works. Same thing with x squared minus 10, x squared plus 9,322, right? All of those, y prime would still be 2x. So on a lot of these, there's not just one possible y, right? There's a lot of them. That's why I have made it such a big deal in this class. And for those of y'all who had me in Cal 1, I made it such a big deal. You have to always put plus C, right? So the general solution is the one that includes plus C because it's a basic format for every possible y I might have with the plus C. Now, taking it one step more, a particular one is a specific function that satisfies the differential equation given some more stuff. So basically, if I have a point, I can use that point and solve it for C, which is kind of what they did on this example right here, because I have a plus C. So that's what they did there, was solve it for the C. So a particular is whenever I have a point, and therefore I can solve it for the C. All right, so example number 4, we're going to start real basic. Find the general solution of the differential equation y prime equals 2x. Then, once I have that, find the particular solution that passes through the point 2, 7. So, the differential equation there we said was y prime equals 2x. So first things first is they want the general solution. So the basic format. Okay. So I know that y prime is equal to 2x. So what that means is I know that the derivative of y is equal to 2x. If I know that the derivative is equal to something over here, how I go backwards and find y is take the antiderivative. So do that. Antiderivative of a derivative cancels out, so this is just y equals, to take the antiderivative of 2x, add 1 to the power, which would make it 2, and divide by that new one. And then, like I always say, remember, do plus c. 2's cancel out, so the general solution is y equals x squared plus c. Y equals x squared plus c. Okay, so now for the particular solution, we're going to actually solve it for the c because they tell us it passes through the point 2, 7. So I'm going to plug this in to the y and solve it for c. So 7 is my y, so 7 equals, and my x is 2. 2 squared plus c. 2 squared is 4, so this means 7 equals 4 plus c. So to solve it for the c, subtract 4. Subtract 4, and you get 3. So the particular one is y equals x squared plus 3. That's my particular. This is the general solution. This is the particular for that point. Once again, it just means solving it for c. Another example, example number 5. Example number 5 wants us to find the general solution of the differential equation y prime equals 4x plus 3. And then after I do that, then find the particular solution that passes through the point 1, 7. So for the general, again, I have y prime is equal to some stuff, right? So just take the antiderivative. That gives me y over here equals, add 1 to the power, makes it a squared over 2. With 3, it just becomes 3x plus the constant. 2's cancel out, so you end up with y, which would give me 2 left over. 2x squared plus 3x plus c. This is the general solution. Now for the particular, we're going to plug in our point. They give us the point 1, 7. So 7 in for y, 1 in for x. 7 equals 2 times 1 squared plus 3 times 1 plus c. So that means 7 is equal to 1 squared is 1. 1 times 2 is 2. 3 times 1 is 3. 2 plus 3 is 5. So 7 equals 5 plus c. Subtract 5 and you get 2 for c. So the particular would be y equals 2x squared plus 3x plus 2. That's the particular. Again, these few we did were like basic as it could possibly be. As we move on, we are going to learn harder ones than just this. All right, so another term I've got to know. It's kind of like finding the particular, but it's just another word. So the definition's right here. A differential equation together with one or more initial values is called an initial value problem. So basically, it's just like this, where it's going to give me a point, and I'm going to use it to find c, is what it means. Example number 6 says to verify that the function y equals 2e to the negative 2t plus e to the t is a solution to the initial value problem. Y prime plus 2y is equal to 3e to the t. with y of 0 equaling 3. So the reason on values you always see a t is because most of the time I'm dealing with time. And so that's why sometimes you'll see t, sometimes you won't, but it doesn't really matter because it doesn't affect what I do, right? It may be t, it may be an x, it may be something else. Okay, so again, we're verifying that the differential equation y prime plus 2y equals 3e to the t such that y of 0 is equal to 3. We're going to verify that the solution is y equals 2e to the negative 2t plus e to the t. So again, we are going to plug this into this and make sure that it's true. Okay. So first things first, I have y, so I need y prime. So y prime is going to be equal to the derivative of e. Remember, e just stays e, so that's just going to be e. But by the chain rule, I need to times that by the derivative of negative 2t, which is negative 2. Negative 2 times 2 is negative 4. And then this one is really easy. The derivative of e is just e. So plus e to the t. That is the derivative of y. So now plugging that in, y prime we said was negative 4, e to the negative 2t plus e to the t plus 2 times y, which is 2e negative 2t plus e to the t. Let's simplify this, see what happens. First part, nothing changes. Distribute by 2, so plus 4 e to the negative 2t plus 2 e to the t. Negative 4e to the negative 2t plus 4e to the negative 2t cancels out. E to the t plus 2e to the t is 3e to the t, which is exactly what I wanted. So that's good. But they also give me a point, so I need to also make sure this point will work. So if I plug 0 in, I should get 3. And let's see if that happens. So plugging 0 in gives me 2e to the negative 2 times 0 plus e to the 0. My power here would be 0. E to the 0 is a 1. 1 times 2 is 2. Plus e to the 0 again is 1. 2 plus 1 is 3. So that also is good. So again, the whole point here is I just wanted to show you what I mean by the solution. I want to make sure that it works over here, which is what we did here, and that my point will also work. So now let's practice solving some. Again, this is the same thing as finding the particular solution. So same process as examples 4 and 5. Example number 7 says solve the initial value problem. Sorry, a pop-up just popped up on my screen, so hope everything is still good and I'm still recording. Okay. Example number 7 says solve the initial value problem y prime equals 3e to the x plus x squared minus 4 with y of 0 equal to 5. So we know y prime equals 3e to the x plus x squared minus 4, and I want y of 0 to be equal to 5. So if it gives me y prime, we know to find y, just take the antiderivative. So do that. That gives me y on this side. What's really nice is e just stays e, so this just stays 3e to the x. Add 1 to the power, and then divide by the new power. Gives me x to the third over 3. This gives me 4x. And then remember, always do plus c. This would be the general solution right there. But they give me a point, which means I need to solve it now for c. So plug 0 in for x, 5 in for the y, and we get 5 equals 3e to the 0 plus 0 cubed over 3 minus 4 times 0 plus c. E to the 0 is 1. 3 times 1 is 3. 0 cubed is 0, so that's 0. 4 times 0 is 0. So we're just left with plus c. To solve this for c, subtract 3, and you get 2 equals c. So the answer here, y equals 3e to the x plus x cubed over 3 minus 4x plus c, which was 2. There we go. One more example, example number 8. To solve the initial value problem, y prime equals x squared minus 4x plus 3 minus 6e to the x, with y of 0 being equal to 8. So let's do that. Prime with y 0 equals 8. Okay. So once again, they tell me y prime, so I can use that and find the y. Integrate both sides. That gives me y on the left side. X squared, remember, add 1 to the power, then divide by the new power. Same thing here. Add 1 to the power makes it x squared over my new power, which is 2. 3 just becomes 3x, and then we like e because e just stays e, so this is just minus 6e to the x. And then remember, don't forget plus c. Simplify this because 4 divided by 2 is 2, so that means we get x cubed over 3 minus 2x squared plus 3x minus 6e to the x plus c. Okay, now plug in our point. 0 for x, 8 for the y. So 8 equals 0 cubed over 3 minus 2 times 0 squared plus 3 times 0 minus 6e to the 0 plus c. 0 cubed is 0. 0 squared is 0. 3 times 0 is 0. E to the 0 is 1.